Okay, so just to quickly define some terms, when we're talking about flexible design here, we're talking about code that's easy to modify and extend. Pieces of behavior in the code you want to be able to reuse elsewhere, and in order to extend your system easily, you need to be able to understand it. When you make changes in the system, you don't want those changes to be intrusive changes, and as you expand the system, you don't want to explode complexity. Any number of reasons why flexible design matters, but a few that we usually like to focus on are when you're expanding teams, you need to be able to onboard developers quickly, so they have to come up to speed on the code. When market conditions change, you're going to have to respond quickly with unanticipated feature changes. When you introduce new functionality, you need to be able to do so safely without introducing a bunch of bugs.
So when we're talking about testable design during this talk, we'll be talking about unit testing. Some of the ideas do extend to components and subsystems, but we'll focus on unit testable code. So what does it mean to be unit testable? We need to be able to instantiate a class and its collaborators in an easy manner. We want to be able to set it up into the desired state and then drive the code through each of the execution paths and then witness the effects to ensure that the code is behaving the way that we expect it to. So what makes a unit test good? Well, we want them to run quickly, and in parallel, whenever we'd like them to do that, we'd like them to be hermetic, meaning they need to be isolated one from the other. When we have an error, we'd like to be able to find exactly what causes that error. We don't just want to know there's a regression. We want to be able to pinpoint the code that's causing the problem. Good unit tests are easy to write and to read, and they validate not just the happy paths, but also corner cases, exceptional conditions, and error cases. So I think we're here among our fellow test engineers and people who are interested in testability. But the reason that it's important is we want to isolate pieces of behavior for validation. When a test breaks, we want to see exactly what went wrong, and we don't want to have to jump into the debugger to try to solve the problem of why did this test break. At Google, we have a motto, which is debugging sucks and testing rocks. So a brief aside, we're not trying to say that end-to-end testing isn't important. It absolutely is. We love unit tests, but we also understand the need for end-to-end tests.
So as we proceed here, what we're going to do is look at a series of common design choices that need to be made. For each one, we'll introduce a situation. We'll take a look at one possible design alternative that has poor flexibility and poor testability. We'll explore why, and then we'll introduce a second design alternative that improves both of these characteristics.
So we'll start off with running an example. This is a hypothetical application, the Google Cacophony. It is a way for people to collaborate on musical compositions. And it needs to do a lot of things. We need to process music change requests, parse user preference files, apply some audio filters, turn this into MIDI files that are playable, and send results to the users. So the first common situation, we have to answer the question, how large should our classes be? We often deal with developers who say, I really don't want to introduce a lot of little tiny classes into my system unless there's value for doing that. So our first design is the not recommended design, and that is to put several behaviors in a huge class. We've got a music server, and you can see by this comment, it does, thank you. You can see from this comment, it does all kinds of things. It's processing music change requests, parsing preference files. Everything that we have under the sun is in this piece of code.
So this isn't a really good choice in terms of flexibility. Reuse is inhibited because any piece of behavior in the system is tucked away inside this one big class. If you'd like to use it anywhere else, it's unavailable. Also, suppose we're wildly successful and we branch on beyond MIDI files. We want to start adding MP3s, waves. Our parsing is going to get more complex. We've got audio filters that we're adding every day, new instruments. That complexity has to go somewhere. And if we've got multiple responsibilities in the same class, that's where they're all going. Also, conditional complexity is likely to explode inside this one large class. Let me, before I move on to some other flexibility concerns for this design, let me just take a brief aside to say global data is bad. Do we all agree we'd like to minimize the use of mutable global data in our system? I see some hands up. Okay, yes, reduce the use of global mutable data. But what's the problem with global mutable data? The problem is what Michael Feathers calls a spooky action at a distance. If any code throughout our system has access to be modifying this data, then it means the code that depends on the data is difficult to understand because the data is going to be shifting underneath it, and it's difficult to tell who did that shifting. Where did the change come from? Why am I bringing it up? Because if we've got multiple responsibilities housed in a single class, then we've really created a system where the fields in that class are essentially global. Or maybe it's just a portion of our system, but for every responsibility that has access to every piece of data in this class, any method could change any field. So we're in kind of the same situation as with global data we were in the large. We've lost application within this space that we've created. It's the same situation for private methods. If any method in this large class can call any private method, we have to ask ourselves how private is private.
We also have to face that the testability of the system isn't very good either. Just imagine your input is a change encoded in an RPC, and your output is an MP3 file. So trying to unit test this is really essentially an end-to-end test. And we have this input coming in, various things are happening inside this large class. The output is an MP3 file. How do we validate that? We're probably going to make some golden files, some well-known files that are good. We're going to have to compare these two files to say, is this the right answer? And anytime we have a regression, it's really tough to tell where do we go. We go right into the debugger. Where did the problem happen? Well, let's whip up the debugger and we'll find out where it is. Also, if you make intentional changes that should alter the final MP3 files, you have to create new versions of your golden files. And if you have to change a lot of those, that's going to be a real pain. Another thing is the notion of safety. When we are changing our code, we want to just change the code, and we'd like the test to be a safety net. If we have to change both the code, the production code, and the test code together, then we've lost that safety net aspect. We may make mistakes in doing these changes in two places.
Okay, so let's look at a second design alternative. Instead of one large class, let's define crisp small classes with distinct behaviors. Request handler, a preference reader, preference parser, a music mixer, each doing just one thing. Sometimes this is called single responsibility principle. Sometimes it's called separation of concerns. We've improved flexibility with this design. Each of the classes is easy to step back and understand as one conceptual unit. In the larger class where we had all these behaviors mixed, we lost the power of object-oriented programming. When we split the behaviors up into crisp, distinct units, we get that power back. Object-oriented languages generally provide us with natural features for encapsulation and polymorphism. It lets us, when we have variable behavior to accommodate, which is always the case with flexibility, it allows us to further subdivide our behavior into siblings in an inheritance hierarchy that we can install or even swap dynamically.
Our testability has also improved now with our smaller classes. The test can be more focused on each individual class. It's much easier to test unusual or exceptional behavior. We can drive our small classes through the various paths, and we don't have to go that kind of big end-to-end. The input for each unit test is really easy to supply. We don't have to start with a change request, and then our outputs are an MP3 file that we have to check against a golden file. We'll have smaller targeted focus tests. An example would be, how would we test the audio filter selection is always correct? With the first design, with a large class with a lot of behavior, we would need to construct golden files for every different kind of audio filter selection. That's going to be difficult to do, and it's much easier in our second case, where we have these smaller classes. You can just test one piece of it. We can test that a filter selector is returning an appropriate filter depending on the filter specification.
Okay, let's move on to a second common situation. Classes need configuration data. That's true of just about every system, right? The question, though, is how should we supply this information to each of the classes that need it?
So in this case, we're going to have a user that directly reads data from a file. So internally, the user is reading the file, parsing it, and creating either a configuration object or some kind of data structure from that information. And a user has other responsibilities. This isn't the core responsibility of it. So this is a smaller violation of single responsibility principle. But we see this so often that we wanted to call it out specifically. And you've probably all seen this kind of code. We've got a user. It has a preferences field. We take the preference file, we parse it, and then we store the resulting data into the preferences object. Later on, we do something with the preferences.
Okay, so this gives us some flexibility concerns. If you want to change this file format, how do you change it? You have to go into the user code and make intrusive changes there. If you want to move on and support multiple versions of preference files, you're going to be adding conditional logic into your user. User is tied to the file system. Suppose that our cacophony service becomes wildly popular, many users, and we need to offload preferences to a preference server. We want to communicate with the preference server via RPCs. Again, we're going to be going into user, we're going to be making intrusive changes so that it can depend upon the RPC mechanism for its preferences instead of the file system. And suppose that elsewhere in the system, these preferences would be useful. Well, we've buried the reading, parsing, validation inside the user code and inhibited reuse with this design.
This design also has poor testability. We wanted our tests to run fast, but we know that tests that hit the file system are slow. And to set up our tests, we're going to have properly formatted files, one for every kind of preference or every combination that we'd like to have. And then if the file format changes, let's say we have to have a new piece of required data, we have to go to every test file and modify it.
Okay, so preferred design for this, instead of having user tied directly to files, we have dedicated code elsewhere that reads, parses, and validates the file, and we install the constructed preferences into the user, direct injection. Now, so far, all we've done is we've moved the problem from user somewhere else, and later in the talk, we'll be explaining that somewhere else and how to solve that as a problem. We've improved our flexibility, though. If we have changes to the file format, user is insulated from that because it only sees the constructed preferences. If preferences come in from another source, user is insulated from that. It remains stable.
And now with our new design where we don't have to go to the file system, our tests are going to run a lot faster. It's much easier to construct a preferences object and create different variations for testing in memory. And also, our tests are no longer tied to that file format. So if the file format changes, our tests don't actually have to change. As an aside, this is true for general kinds of input. The same reasoning applies for files as for raw sockets and RPC mechanisms, et cetera.
Okay, let's move on to yet another extremely common situation. We have stateless services and utilities throughout our server, and classes throughout the server that need access to those. The question is, how does a class that needs the service get access to that behavior?
One choice that we often see being made is to access the service via a static method. It often seems like a good idea at first. Hey, that's really easy. The service is globally available. We just can call the static method. We don't have to create an instance. And that's going to be really easy to test, right? In this example, we have a musical score. And when the score is changed, we'd like to inform authors via email. So we came up with this great idea to we'll have an email sender, and it'll have a static send method. We can just easily call that and give it the message.
Okay, we've got a flexibility concern. What happens as we want to support additional ways of notifying an author? We were notifying by email before, but now some users want text messages. Others want a Google Buzz or a Twitter tweet. Here's typical code that we see feature developers write to solve this problem. We're switching on the preference of the author, or of the musical author, whether they want text message sent to them, whether they want email sent to them. And for each of these different possibilities, we're hard coding a connection to a different static service. So this isn't really a good choice because we've increased the complexity, and there's really no easy way to use polymorphism to solve the problem. What we'd like to do is we'd like to have just a single interchangeable way of doing send notifications.
This design also has poor testability implications. So naive testers might think this improves testability. You don't have to instantiate the service, you can just test it. But the problem is the consumer of the service can now not be tested in isolation. It's directly tied to that service. And often these services are complex or expensive, and we don't want to do that in unit tests. We said we want our tests to run fast. Also, trying to prevent an email from actually being sent in this first example takes extra work. Typically, we'd have to put some code inside the email sender that's for testing. We'll have a little flag that says, if testing, don't actually send an email. That's pretty bad. And we'd like to, a brief aside to have a caveat here, we're not talking about simple stateless utilities. There are things that are fine to have, like math absolute is totally fine as a static utility. We're talking about more heavyweight services.
Okay, so instead of having these brittle static connections, our preferred design is to make the service instantiable, or at least to have a class that we can instantiate that accesses the service on behalf of the consumer. This allows us to take advantage of an inheritance hierarchy to unify the variant behaviors, and we can inject a subclass of a sender interface into the musical score. The code looks like this. Somewhere else, dedicated to understanding an author's preference, we construct a sender subclass, and then musical score is very simple. It just takes a sender. It doesn't care which kind of sender is installed. Send update no longer has the conditional logic that we saw before. It just, whatever sender was installed in its constructor, when it's time to send an update, it sends the message through that sender. And again, at this point, it just looks like we're moving the problem one level up, but we'll be talking about that in a minute. So flexibility has improved now. Musical score doesn't know every different way in the system that an author might want a notification sent to them. As I said, conditional logic has been removed, and adding new sender types is not going to make us go and make intrusive changes in the musical score. It remains stable to that kind of change.
Our testability is also improved now. Now we have a seam where we can insert fakes or mocks where we'd like to. This helps us avoid those expensive operations that we had been statically tied to, things that may take up a lot of time or memory, or have avoid undesirable side effects like actually sending an email every time we run our test.
We also can simulate exceptional cases and error cases when we have fakes or mocks. Instead of just depending on the service to maybe fail for us sometime, we can inject a fake that simulates a failure.
Okay, on to another very common situation, getting data to consumers. So we have classes throughout the system that need some kind of data. Often it comes from command lines, initialization files, maybe directly from a request, or anything derivable from those sources, maybe via a data store. And each of the classes in the system really only needs to work with one or a few, maybe zero, kinds of this data.
So what happens when we very first start with the system, we might just weave one data item from main down to the classes that need it. But then our system gets larger, and now we've got second and third and fourth parameters, and we need to weave those all the way down into our various classes. As the system starts using more data, we start tacking on additional parameters, and it gets pretty ugly pretty fast. We don't want to have to pass 50 parameters in every method call. So there are a few designs that people tend to use for this, and we don't recommend any of these. As the systems grow, we see sometimes people will bundle their data into a context object that's passed throughout the system. Or chunks of data are packaged together into classes that are already widely known in the system. And then the other is the bucket of static data, which is a problem that we've already discussed in terms of global data.
Okay, so design 1A is the context object. It's a big collection of data that we end up passing throughout the whole system. Often we have, if we think of our system as a large aggregate structure, this context is passed from parent to child to grandchild down through the system. Many of the nodes touching it only need to touch it to pass it around. Others receive it, this context object, and they reach into the context to grab the data that they need. There's some flexibility concerns with this design. So the context object is so widely known throughout the system that it might as well be global data. All the problems that we said we had with global data are also problems with this extremely widely known context object. We'd also like to build our system in such a way that we can look at a class, look at its constructor and public methods, and be able to understand what other parts of the system it collaborates with and what kinds of data that class makes use of. When we're passing around this large context object, we've lost some of that. You don't know whether a class receiving this context object uses it at all, just takes it so that it can pass it down to a child class. And if it does use it, you don't know why, just by looking at the surface of the class. You don't know whether it needs access to a country code or not. We've also inhibited reuse severely, because if we've got classes that depend on this particular context object that maybe would be useful elsewhere or in other systems, it's really difficult to reuse them there because those other systems aren't going to use the same context object that the class that we're passing this through is brittly tied to.
So the other choice is what we're calling holders, and basically it's overloading a well-known class to carry extra bags of data. We often see this with something like a user, where this user object is needed in a lot of the system, and we pass this data clumped up with the user. And what happens is we add a little bit of data to the user, and then that starts to get pretty big. So then we split that off and we say, okay, well now a user has some preferences, and that starts to get pretty big. And so we say, well, let's have a location data. And then inside of that, well, that's pretty big. Let's have it have the country code. So then when we have this user being passed around, classes like account that require a country code have to dig it out of the user. And what this looks like in practice is an account takes a user, it wants a country code, but it goes to the user and it gets the preferences out. And then it takes the preferences and it gets the location data out. And then it takes that location data and it finally gets the country code. And that's the piece that it really wanted.
Has anyone seen this code? Okay, everyone in the room has seen this code. Okay, this code has flexibility concerns. I already said public methods don't really reveal what's going on. Also, we've got this code that Tracy just discussed that digs down into the structure that we're passing around. It's often duplicated. If we've got two places in the system that need the country code, we often see the same dotted code to dig it out. And this digging code also locks the structure in place. So if we were to decide that our system would be better factored if country code were stored in another way or somewhere else, we've got maybe 50 places in the system that are hard-coded to this dotted representation of the structure that it's currently in. Refactoring is going to be severely inhibited.
This is also a problem for testability in both of the cases with the context object and these holders. Our tests are unnecessarily complicated. We have to do a whole lot of setup to get these pieces of data into this nested location only for the purposes of allowing the class under test to basically dig it all out. What that looks in practice is we've got a test where we've got an account and it needs the country code, but it also needs to get it out of the user. So we have to make a country code, a location data, install the country code in the location data. Then we have to make the preferences because the location data is part of the preferences. Then we have to make the user and install the preferences in the user. Finally, we can give the user to the account. And all of this just so it can do that dotted digging out of this data to get the country code.
And we tend to see this kind of code in tests repeated over and over again. So there's a preferred design. Instead of nesting the country code way down in this structure, we're going to say we should just pass the country code directly to the class that needs it, in this case, the account. And that may sound like I'm just being flippant, but at several points, we've said we're going to get to something later, and the time for later is now.
So we're going to talk about system assembly, and we're going to use a different example than our Google Cacophony server, because this one is something that people understand how things are put together. So if we're going to try to construct a car, and it needs a windshield and an engine needs spark plugs, we're going to look at two ways to assemble the system. One will be top-down, and one will be bottom-up. So the earlier design choices were poor, and the reason that we ended up with these is due to this following structure, and it's the top-down assembly, where we say, okay, we're going to make a car, and inside the car's constructor, it's going to construct its own collaborators. It's going to new up an engine stored in a field, it's going to new up a windshield and stored in a field. What happens when we say new engine? Well, engines need spark plugs, so in the engine's constructor, it's going to conveniently make its own spark plugs, put them into a set of spark plugs. Now, constructing a car is really easy, right? All I have to do is say new car, and I get a fully assembled car. I get the full object graph. But the problem is that changing the parts inside the car are really hard.
Okay, so this is a brittle way to assemble our system. Suppose that we decide that we want a high-performance spark plug instead of a standard spark plug. Where do we have to make that change? We have to go directly into the engine. The engine needs to know there are two kinds of spark plugs. It's going to have conditional logic, in this case, in its own constructor to make a spark plug selection. And in some cases, it has to do even more work to additionally configure its own collaborators. Just moving spark plugs one level up to car doesn't help, because then car needs to know about both kinds of spark plugs to be able to pass those down into an engine.
As you can imagine, this also has an implication for testability. When we want to use a car in our tests, we get the entire object graph. We don't have any choice, that's what you get. And that might be expensive to make, and so every test is going to have to create this entire object graph, even though we maybe don't really want that. If we want to have test versions of our collaborators, there's no seam, there's no way to get those in there. Everything is taken care of under the covers. We're stuck with the standard windshield, the engine, and the spark plugs.
Okay, so design 2, which we prefer, is bottom-up assembly. Instead of having every class construct its own collaborators, we'll have dedicated creation mechanisms off to the side. In a manual situation, this implies a collection of builders and factories. You may be fortunate enough to be able to use an automated framework like Google's Juice or Spring. But the idea behind it is, instead of creating a parent that creates its child, that creates the grandchild, we're going to create the grandchild first. We're going to start from the leaves. And once we've created spark plugs, then we can create an engine that we just pass the spark plugs into. If we have a dedicated spark plug factory that knows how to decide whether we're using standard or high performance spark plugs, then it creates the kind of spark plugs we need and can install those into the engine. No conditional logic in the engine, it just uses spark plugs. Once we've created the engine, we can create the windshield off to the side, and now it's easy to construct a car just passing in the already created and populated engine and windshield. So flexibility is improved because now we don't have to make intrusive changes into classes like engine and car when we have variant behavior to support in their children.
It's also now easy to test our pieces in isolation. We're not stuck with that big object graph. We can create the pieces as we like. It's really easy to create fakes and mock collaborators and inject them into our system under test. So we can make a car with a fake engine that refuses to start, and we can test out that behavior. We can make spark plugs that actually validate if it was asked to fire by the engine. This lets us push through all the different conditions, which is what we want for our tests.
Okay, let's move on to another extremely common situation. We have clusters of behavior that change together, and multiple sites throughout the system, perhaps in the same class, perhaps spread across classes, that use these clusters of behavior. An example to make this clear, in the cacophony server, we have different account types: free, basic, and premium. And depending on what kind of account we're working with, a music mixer may need to place some limits. Maybe for a free account, we can only afford to provide the collaborators with, the users out there, with a 10-second duration clip. Basic account, they can get a minute. Maybe it's an unlimited music clip for a premium account. We may contract with third parties who provide filters and instruments for us, and depending on whether you're free, basic, or premium, it could limit either access to or maybe the quality of a filter or an instrument that we'll use.
So the first design choice is, again, our not recommended choice. We have a director class, and it has a music mixer and an account type as fields. And when we want to have each of these features, we go and we do some conditional logic for deciding what the account type is and then what the behavior is. So if the account type is free, we'll ask the mixer to truncate the audio short. If the account type is basic, we'll ask the mixer to truncate the audio in the longer section. And if it's a premium account, we won't ask for truncation at all. We also, still inside the director, will have setup for instruments, free and basic and such. And similarly for applying our echo filters.
Okay, so this design choice is poor in terms of flexibility. Anytime we want to make a change to add an account type, we're going to be extremely intrusive, because for each clause, we're going to have to go and add a new conditional statement for how we handle mega premium accounts. The logic for how we handle a given kind of account is scattered around. So if we wanted to step back and understand how does our system respond to when we're working with a premium user, you can't just look in one place. You have to look at behavior that's dotted throughout the conditional clauses. And this kind of code invites bugs. When you're making a similar decision over and over and over again and switching on that decision, you're asking for a mistake to be made. In fact, we just got a call from hypothetical support on our hypothetical server, and they tell us that we've just been charged by our third-party vendor for a hypothetical extra million uses of premium echo filtering. Let me back up here and say, here's what happened. In one of these conditional clauses, we said if account type equals premium, we're going to apply the free echo filter, and the last fall-through case, which should be free, is applying premium echoes. So we made the same decision in multiple places. In one place, we got it wrong.
Testability is also impacted when we want to validate that we're doing the right thing. The director has to call each correct mixer method, and we have to make sure that we do that for every account type at every feature. Otherwise, we'll have these bugs like we just found. So we need a mock mixer to expect the free or the basic or the premium versions of every single feature. What that means is a combinatorial explosion of tests. We've got a cross product of features and account types. We've got free, basic, and premium, and then we have to cross that with truncation, filtering, et cetera. So a three-way decision at each of 5 features means 15 tests. As soon as we add a new account type, we have another test for every feature, or if we add a new feature, we need another test for every account type for that feature.
So we have a preferred design decision for this, and that's isolate the free, the basic, and the premium behaviors each into a separate class and create an inheritance hierarchy to unify the interface to those classes. In this case, music mixer interface with one method per feature. It looks like this. So off to the side, we're making a selection of which mixer to use. That selection is made just a single time in one place instead of repeating our conditional logic over and over for each feature. And then when it's time to use a feature, we get to delegate to the properly selected mixer or cluster of behavior. This makes it really easy to support new account types because, again, we've eliminated the conditional logic from inside our director. All we have to do is create a new kind of music mixer and pass it in. We also, with this design, have addressed the consideration of the logic that was scattered about. Now we have a single place we can look and say, how do premium account works? The directors become simple, and the bug that we saw a few slides ago is almost never going to occur.
This also helps us with testability. We've now eliminated the combinatorial explosion of tests. We don't need multiple tests to ensure that the director is calling the appropriate music mixer method because now we've consolidated that into single methods per feature. We may end up writing a test that validates when we have a premium account, we get the appropriate mixer, but it may already be tested by our end-to-end tests. So we'd like to go from the specific to the general. Why does this work? There are 3 foundational pillars of object-oriented code: encapsulation, loose coupling, and high cohesion. And as an aside, a strong use of polymorphism supports both cohesion and encapsulation. So let's go back through each of our examples. We had the music server with most of the code in one class. We said that wasn't very encapsulated at all. As soon as we split that into multiple classes, now we have better encapsulation, and we have high cohesion if we've made good choices for splitting up that behavior into the appropriate classes. When we had a user reading the preferences file directly, we weren't encapsulating our file parsing or the format of the file. And so we had a high coupling between the user and the file and its format. When we instead inject the preferences data right to the user, we've now encapsulated the file parsing and format somewhere else into a file parser. and we've decoupled the user from the file and its format. We had the musical score where we were using the static sender service, and we ended up with some very tight coupling between the musical score and all of the sender services. The musical score had to know the concrete type of all of these senders. That's not what we want. We'd really like things to be loose, and so we can easily inject a different kind of sender. We can create new senders. We want loose coupling between our musical score and our sender. We want only to know about the sender via the interface. We talked about a context object and a holder for bringing data to the various kinds of classes throughout our system. The problem with the context object and the holder is there isn't any encapsulation. We're digging into all of these pieces, ripping out the parts that we want. We also end up with tight coupling. We have all of these classes throughout the system weaving this context object through. They're all dependent on either the context object or, in the other case, the user. And we end up with low cohesion. The context and the user are basically dumping grounds for information. The things don't necessarily go together. It's just convenient to put it there. Instead, when we inject exactly what the class uses, we don't violate encapsulation anymore. We're not digging into the user to get the preferences, to get the location. And we also have loose coupling. We only tie classes to the collaborators and the data that they actually use. We talked about system assembly and the preference for bottom-up. When we have top-down assembly, with the car creating the engine and newing up all the pieces behind the scenes, the assembly logic is distributed throughout the system. And we also have some very tight coupling. A car has to know about all the concrete engine types because it's going to be creating them, similarly for the engine and the spark plug types. When we go bottom up and we have factories and builders to help us out, we separate the way that we build the system from the business logic. And we also end up with much looser coupling. A car only knows the engine by its interface. It doesn't know all the concrete types of engine. And in the music mixer, we had the director with the music mixer and 3 accounts. The behavior for a given account type isn't cohesive. It's scattered throughout the director. And it's also sort of scattered throughout the music mixer, as we saw there were different methods for each feature. When we instead go with the 3 mixer subclasses, we end up with encapsulation. The director doesn't even know about the account. All it knows is it knows the mixer by the interface, and somewhere else is making the decision of which mixer to use. We also have much higher cohesion because the behavior for an account type is together in one of these mixer classes. So the common themes here are encapsulation, coupling, and cohesion. And if we optimize for these, we get an increase in both flexibility and testability. We end up with units of behavior that we can exchange, we can vary, we can reuse throughout other parts of the system. And our testing is much easier. We can have small focused unit tests. We can push our code through the various paths. We can easily substitute collaborators, so we can do fakes and mocks.
And working with many people, many teams, is that you can't just have a single canned argument or prepared speech that's going to convince everyone. Every case is unique. People care about different things. They're in different situations. You have to tap into the unique situation you're working with in order to actually influence an engineer's design habits. There are many right convincing arguments, and not every argument is going to work in every case with every engineer. You need to understand the developer or the team, what their motivations are. You have to understand something about the context that they're working in, what has worked well or poorly in the past for them, what kind of challenges they have in front of them. The first thing you want to understand is what motivates the individual. Some feature developers, they care about testing. And you're going to be able to make a strong argument just in terms of how they can improve their ability to write the tests that they want. Some developers, well, you know, maybe they'll write a test if they're kind of prodded to by you or their colleagues, but they don't want to think about testability when they're designing code, but they are motivated by producing code that's flexible. So you want to understand that and tailor your argument to the individual. You also want to know something about the particular code that they're actually working on. You want to take into account how a specific individual learns. Some people are really good with theoretical explanations, and some really, especially a lot of engineers, want to see something very concrete. They want an example, and they'll generalize themselves. If you're working with a theoretical learner, you might need to first establish some common ground, like we did introducing the notion of global immutable data that then allowed us to discuss related cases like multiple behaviors housed in a single class. If it's an individual that learns best by example, you're going to want to look in their code base, hopefully the code that that individual has written, and find an example where you can point out the kind of design situation that you're talking about and make your points using their code. Then you want to select a strategy. If it's someone who can be influenced by testability arguments, look through the code and find a test that they can agree they'd like to write but is inhibited with the current design. Show how the alternate design that you'd like to propose solves that problem. Maybe you even work together toward the solution so that they have that sense of discovery instead of just being told. If it's someone motivated by flexibility, find a feature that is currently inhibited in terms of flexibility. Maybe something that was already implemented but is really awkward, or a feature on the backlog that is going to cause problems that you can show the difference between two design choices and how the one that you suggest will allow that flexibility to be implemented easily.
So in conclusion, we hope that you'll take these ideas and generalizations to analyze your own code and to apply flexible and testable design and influence with your teams to do likewise. So we have some time for Q&A.
Hi, Russ and Tracy. I have a question with respect to encapsulation and its impact on testability. Because encapsulation was one of the common threads in your discussion through the PPT. So encapsulation itself makes only a subset of the methods or the properties available as a part of the contractual interface, thereby limiting the testability. So how do we deal with encapsulated classes? How do we test them thoroughly?
So often when people talk about encapsulation, they're really talking about taking a large part of the system and hiding it behind a narrow interface. And what we were showing with the leading example is that's not really encapsulation. When we talk about encapsulation, we have to talk about encapsulation of one set of code or data with respect to other pieces of code and data. And if what's happened is we've walled off a large portion of the system behind a narrow interface, and there aren't seams between those individual pieces that we can use maybe represented as classes that we can instantiate separately and exercise separately in tests, then within that large circle containing all that behavior, it's really not encapsulated. So it's a false claim that that's true encapsulation because so much code is sitting in that area, not encapsulated from itself. Multiple responsibilities that have access between themselves that they shouldn't have.
Private methods as well. Right, so the question is, the moment you mark a test private, now there's a question of testability. So what we would like to do is test our classes solely through the public interface. And why is that? Because as soon as we mark something private, we're saying The details of how this works is not important to the outside world, and we should feel free to change private methods without regard to testability, because we shouldn't be testing those, right? We want to only drive our classes using tests as another client, right? So we've got collaborating classes, and we don't want to have two classes in the production system basically knowing the details of the private structure. Similarly for our tests, we'd really like to only test through the public interface as much as possible. Now, sometimes what happens is you end up with a class and it's got a private method and it's doing something very complicated, right? And gosh, we'd really like to test that. Sometimes what that ends up telling you is we should take that, pull that out into a class. And it's okay to have small classes and have that responsibility be something that we can test and use collaboration here to pull that piece out if it's really important to test and it's sort of tucked away behind a private barrier.
Yeah, in general, if you're feeling like you need to test something that's a private method, that almost always means that your class is doing multiple things, and one of those things is that private method, or a cluster of behavior underneath that private method. Good class decomposition says isolate that behavior in its own class. In this case, maybe we're talking about the gang of four strategy pattern.
Hi, this is a question regarding the country code example which you had taken. So we basically moved the country code out of which was designed as the proper hierarchy to a place where it was being referenced to. So is that a right solution, or should we more so look at implementing a global kind of class or function which provides me that hierarchy access? Like suppose on the user level I'm going 5 hierarchies down, I can take that whole hierarchical access and move it into a say global function which I could then use. That way I not only solve the problem of in case I change the structure, I change it only in one place, while also sticking to that design which we had created. Because maybe sometime down the line, the same country code might now be required by some other class where we had initially designed it for.
Right, so you're proposing a way of trying to reduce the duplication of how we dig in and retrieve something like the country code. But that doesn't solve all our problems. For instance, Tracy discussed the code that we're going to have to write in our tests just to create the structure that eventually inside the test we'll be digging the country code out of. So we can add extra code, extra complexity to reduce some of our problems, but we can eliminate the problem by inserting the country code directly into a class like our account. And in fact, the other flexibility problem that we discussed was we want to be able to look at a class-like account and from the surface, from its public interfaces, say, we know something important about an account. It works with country code. If we just pass it the user, even if now we've got this function that makes it easier to retrieve the country code from the user, we've still hidden what the actual interaction for account is.
Hello. Hey. So first of all, I agree with 99.9% of what you were talking about.
The point
one.
Which is a lot for people who know me. Still, there is one thing right in the beginning when you were talking about the user preferences and you made your argument why they would be pulled out. I suddenly stopped and I made a note. So this flexibility, pulling out the preferences, isn't that encouraging people to do speculative design and speculative coding? So you think a lot of what if that changes and what if that happens and what if that happens.
Right.
But
Okay.
that might introduce unnecessary complexity into your design.
I'm really glad you asked. Okay, so
With pleasure.
So the term speculative generality, and in fact, we're big fans of trying to suppress speculative generality throughout our systems at Google. But there are two different kinds of generalization. One is when you look out into the future and you say, maybe we should implement some fancy specific mechanism for a change that we're concerned will occur. And often that change never comes, and you've written a complex mechanism that you didn't really need. Now you're carrying the extra complexity in your code. It's bad for any number of reasons. But what we're really talking about here are general design habits that we'd like developers to have throughout their development. We, as engineers, and managers, we're tragically bad at predicting the future for some specific change, but we can, at least in the companies that we've worked with, we can be pretty sure change will come somewhere. And that means trying to build your systems with a general level of flexibility so that when that unanticipated change comes, you'll be able to accommodate it wherever it is. Now, there may be some cases where you don't, one of these designs that we suggested is better for flexibility. Maybe you don't implement that right away, but you have it in mind for when the flexibility comes. And part of what we're trying to describe here with this correspondence between flexibility and testability is that when you're trying to influence developers for how they should build their system, if the person you're trying to reach cares about one and not the other, you want to be able to apply arguments for both. And if you're trying to motivate a developer to go with a design that's more testable, and you can also help them see that it's going to assist with flexibility, they're going to be, if they're resistant to testability itself as a reason to modify the design, that may be what it takes to get them over the hump and use the design technique that's probably best for both.
Hey, Tracy, and Russ, it's great talk. Thanks. One query I have is when you create when a class exposes its service interface, right? And so one of the assumptions there is the semantics of the parameters is constant. I mean, what if and this is a query more from the test design perspective, that what if the semantics of that class interface is changing and not the actual variables themselves? Because if that changes, my test case kind of changes. And if I try to understand or learn more about the semantics, I'll be going on and violating basically encapsulation, which is the fundamental of OOPS. So,
let me see if I can rephrase your question and see if this is what you're asking. So we took a bit of artistic license with the sender interface, and we said, gee, sending emails and sending text messages and sending buzzes, well, we'll just send this message. Is that your question, that if we may not have the same kind of data that's actually needed for sending an email versus sending a text message, and how do we then have a common interface for doing so?
Right. I mean, just to take the car analogy which you provided. So if you have the spark plugs and the engines which make a car, and what if the spark plugs and the engine, they do things differently than they were doing earlier? So if that is changing without changing the interface itself, my test case kind of changes, and from a business perspective. So how do I capture that without knowing about the implementation of the class itself? Is there any way to incorporate that?
Oh, is that someone outside?
Oh,
I'm
that's
sorry, I
someone
thought that was
outside.
someone here trying to jump in. So if we had, the follow-on question is, if we had spark plugs and these two different kind of spark plugs and they needed to behave differently, we're kind of in a bad situation. We really, if we're using inheritance, we really need to have these, a unified interface and have that work for everything. And so if we can't make them identical As much as possible, we would try to do that. Otherwise, yeah, we're stuck with sort of this, well, now we're going to have conditional logic to say, well, it's this one kind or this other kind.
But so in the spark plug case, they have different behaviors, but they probably have the same contract through which you use the behavior, and that's what you can establish in the interface. Really, you only need a common method that unifies the two sibling types of spark plug. I think the other case with the senders is a little bit more interesting, and the question of if different kind of senders need different kind of information to do their sending, how do they get it? So there's a couple different ways. One is, and this isn't typically preferred, but you could pass a collection of parameters to each of the senders that was long enough that each of the senders had what it needed, and some received parameters that they just didn't use. Second option is the director could pass, is it the director? Musical score could pass an instance of itself in along with the message and allow each of the senders to come back and get whatever extra piece of information they need. Third option is the musical score could bundle up some generally useful information and supply that along with the message. And it really depends on, situation by situation, which one of those is the one to go with. But in my experience, usually you can find one of these ways to, if the utility, the behavior that varies really is similar, you can usually find a way to provide a common interface.
Is that it? Are we at time? Okay.
Oh, okay. Ankit is telling me we're out of time, but it's been great talking at GTAC today, and thank you very much.